So, in shorthand, if you guys are in a test and you just need a fast way to do this, if you see largest radius, automatically go for the most negatively charged one, and in this case, it's bromine. If you see smallest radius, automatically go for the most positively charged one, and in this case, it's the strontium 2+. But if you want to understand why we go for those, then you guys can just stick around and I'll explain that. But in shorthand, that's what you should go for. But to understand this, we're going to figure out which isoelectronic species has the largest radius based on the positive or negative charge and how that negative or positive charge affects the element and thus its atomic size. So when we see a positive charge or a negative charge on an element, let's ask ourselves, what does that truly mean? We can use any element to compare this. So in this case, we might as well just use the bromine. So we have bromine minus, a neutral bromine, and a positively charged bromine. So each has 35 protons. Because in this case, protons never change. We're only changing electrons. Let me redraw that, sorry. Alright, so each has 35 protons. But here's where this changes. So we have 35 electrons for the neutrally charged one. To give it this positive charge, we're going to have 34 electrons. And because there's a negative charge, that means we have one more electron. So we have 36 electrons. And as you guys can see, if you subtract this 35 minus 36, you get -1, which gets us that negative charge. 35 minus 35 gets us that 0 charge. And 35 minus 34 gets you a positive charge. So it all adds up. But now let's understand how these affect the atomic size. So let's start with the neutral one. So we see that the neutral one has a 1-to-1 ratio, which means that there's an equal pool of protons pulling electrons, which makes it just this relatively standard size. But this changes when we see this 35 to 36 electron, the proton to electron on this bromine minus. Because now, instead of there being a equal pool on protons to electrons, protons pulling the electrons in, there's now a decreased amount of pull from the protons because now they have to deal with one more electron. So it actually makes it a little bit bigger because now we have more electrons having to be pulled by these protons. And now we can go on over to the positively charged one. Now the positively charged one is going to be the opposite. Now we have more protons than electrons. So these protons can now split up a little bit more for that lost electron and pull each electron a little bit more tightly because they have the increased ability to pull them in a little bit more tightly. So in this, we're going to see that it's actually a little bit smaller. And if we look at this, we can actually compare starting from this. So we see that this right here, this neutral one, is that standard size. If we go to the positive one over here, we see that it gets smaller. And if we go to the bigger one over here, we see that it gets larger due to the negative, that negative charge. So now that we kind of have that set up and we know what's going on, we can now dissect each element and see which one has the largest charge. And some of you may say, well, this has a negative charge, and this has a 2+ charge and a plus charge, but they're all in different spots on the periodic table. Well, in this case, and when we're talking about atomic size, we never just look where it is on the periodic table unless they're all neutral or they all have the same charge. Because if they all have the same charge, we can use the trend where it's increasing this way and increasing this way on the periodic table. And that's increasing atomic size going this way and increasing going down. And we see that with what we just explained a little bit ago, as there's less of a pool as the amount of electrons increase within the element. There's just less of an ability for those protons to hug those electrons and bring them in as tightly as they can. So let's go ahead and do this. So we see that rubidium up here, we see that has a positive charge. So we know that correlates to a smaller size. So we can go ahead and we can get rid of that because we know that there's one more proton than electron in that. Now we can look at the strontium and see that's 2+. That's an even smaller size. So we can get rid of that. That means that there's 2 less electrons than protons in that. So now we can go ahead and we can compare this bromine and this kryptonite right here. So we see that they're right next to each other in the periodic table. Kryptonite has 36 protons and 36 electrons in this case, where the bromine has 35 protons, and in this case, like we said, it has 36 electrons, giving it that negative charge. Now you may even say, well, they each have 36 electrons, what do we do now? And in this case, it doesn't matter because we can see that this is going to have that normal standard size that it typically has, while this is going to go from this typically standard size to having a bigger size because there's this unbalanced amount of protons and electrons. And in this case, since it's negatively charged, means there's one more electron than protons. So it throws off that 1-to-1 ratio, and now the protons have to make up for the ability of pulling in one more electron in, and thus it grows out because they're able to. That being said, we can now discern which one it is. Now we know based off of that it's not kryptonite because we just looked at it, we dissected it, and we just proved that it's still a standard size. And we can go with C,